Hey guys, this is Mr. Anziano. I wanted to record a quick video about one of the problems on the 6.3 practice page. I know you have the answers down here at the bottom, right? There they are. So you can see your answers down here and you can check them that way, but I wanted to go through the process for number 2 because I was doing some things on Desmos and I just made some interesting observations that I wanted to share with you. So I'm going to work out number 2 here. It looks sort of like number 2 on the 6.3, I'm sorry, it looks like letter B on the 6.3 notes that we did in class. That kind of started like this one, right? But of course it's a little bit different, so let's take a look. First of all, we know that we have different bases on both sides of this equation, so we need to take the natural log of both sides. Alright, so what that looks like then is going to look like natural log of 3 to the 2x equals natural log of 5 to the x plus 3. Okay, and so then now we use our power property to move those exponents into the coefficient is kind of what happens here, right? So we're left with 2x natural log 3 is equal to x plus 3 natural log 5. Okay. Now I'm going to combine, actually first I need to distribute that x plus 3 into the natural log 5. So I'm going to leave the left side alone for just a minute. 2x natural log 3 is equal to, now if I distribute the natural log 5 back into both terms in that expression inside of the x plus 3 group, I get x natural log 5 plus 3 natural log 5. And that's just from distributing, right? I distributed that ln 5 into the x and into the 3. Okay. So, what happens next? Well, now I want to move these x ln terms, the x natural log terms, I want them to be together. So I'm going to subtract x natural log 5 from both sides. It'll go away over here, and then on the left side we're left with 2x natural log 3 minus x natural log 5 is equal to whatever was left on the right, which is just 3 natural log 5. Okay. So then basically what I can do here is I can factor out the x from both terms, right? I can factor the x out from both the 2x natural log 3 and the x natural log 5, and so I put the x on the outside of some parentheses, and then I have 2 natural log 3 left for the first term, and just natural log 5 left for the second term. Make sure we include a double set of parentheses there to close off this one. And on the right we still have is equal to 3 natural log 5. Okay, now we're closer to getting x completely by itself, so what I'm going to do is divide both sides by that big natural log expression. 2 natural log 3 minus natural log 5, and then divide this side by the same group. 2 natural log 3 minus natural log 5. Okay. Now we'll have just x on the left side is about equal to, okay, and this is where I'm going to show you what happens over on Desmos. Okay, so let's actually move that tab over here. There's Desmos. So we're going to plug in this quantity right here into our graphing calculator, or scientific, right? If you got a scientific calculator, great, it'll do this just as well. So let's switch back over to Desmos. I'm going to type in 3 natural log of 5 divided by 2 natural log 3 minus natural log of 5. And we end up getting something about 8.214. Okay, so x is approximately equal to 8.214 is how that works. And we look down and notice that that answer does check out. Let's get rid of this box over here. We notice that 8.214 is the answer to number 2 right there, right? So we're pretty confident that we got that answer correct. Okay? But if you didn't have answers to check, what would you do? You'd have to figure out how you could check this by graphing maybe, which you could do. Or you could just kind of type up in the equation. You could put your x value in right there and right there, right? And it should check out. But let me show you what happens with rounding error. This is kind of the point I wanted to make with this entire video. So if we look at the those x values and try to replace these two variables with the solution that we just got for x using our graphing calculator, let's see what happens. Okay, I'm going to type in exactly what I see. I'm going to do 3 to the power of 2 times, instead of x, we're going to replace that with 8.214, right? And we get 68,000, excuse me, what is that? 68,888,697. That's a giant number. Okay, let's see if that's equal to what happens when we plug in 8.214 there. Okay, on Desmos, we are also going to type in 5 to the power of 8.214 plus 3. And we end up getting 68,904,824. Okay, which is actually quite a bit different than 68,888,000, right? It's just about 20,000 off, which seems like kind of a lot, doesn't it? So, is there a way to more accurately check that what we got as an answer is correct? Right? Because when I look at this, I'm not completely satisfied. It's close enough, and we know that there's going to be some rounding error because we cut off a bunch of these digits, right? We only used 8.214, and we cut off this 398,22577 number, so that should definitely affect our answer. Let me show you just how much it does, okay? So remember, we were about 20,000 off here, okay? So I'm gonna delete those, and I'm gonna instead look back at both sides of my equation. And instead of replacing the x value with the rounded answer, the 8.214, I'm actually going to replace those x values with this entire thing. Okay, so I'm going to type in on Desmos 3 to the power of 2 times. This is where it's going to get a little bit messy. I'm actually going to just copy that and paste it right there. Okay, and we end up getting 68,949,000 even 0.7481. Okay, now let's see if that's exactly what we get on the right side over here. And so I'm going to plug in on Desmos. We have 5 to the x plus 3. So we are going to write down 5 to the power of, and this is going to be, again, copy paste. I'm just going to control V here because I already have it copied, and then I'm going to add 3. And notice we get 68,949,000.7481. which is now exact. Okay, so when we're working with logarithms, it's important that we understand first the implications of having rounding errors involved in our answers, and also just how precise we can be if we were to include all of this work that we did over here for the problem. If we were to just have rounded from the very start, if we were to just have rounded natural log of 3 to be some decimal value and natural log of 5 to be some decimal value, we could have gotten really close, but we never would have gotten the exact answer, which is pretty important when it comes down to being precise. So I just wanted to share this with you because I was working through it and I found it interesting. So I hope you did too, and I hope you have a better understanding of why it's important that we are precise, especially when dealing with exponentials and logarithms. All right, have a great day.